Alright, so let's sketch the region here. So that's going to look something like this. Okay, so that's the graph of x equals to 2/3 y to the 3/2. And alright, so this is what we want to do. We want to rotate this region about the x-axis. That's going to result into getting this solid of revolution. Alright, in this case, well, notice that the distance, or well, number one, let's set up a formula to find the surface area. That's called big S equals 2 pi integral. In this case, since we have functions of y, the integral is going to go from c to d, and that's, well, number one, r of y, that's the radius, and times the arc length element 1 plus f prime of y, quantity squared, with respect y. Okay, let's set up this integral to determine what is this going to be in terms of specifically for the radius. Notice the radius is that distance from the axis of revolution to any point on the graph. And notice this distance is vertical because this distance is vertical is going in the y direction. That means this is y. So this r of y is simply going to be y. But unlike the other examples that we did before, we replaced y with the function that we were given, but that's because that was a function of x. In this case, since we are rotating about the x-axis, but in this case, we're given a function of y, this y just remains y. Alright, so let's see about it. So number one, how about we find the derivative of the function? Yes, the derivative of d of y equals 2/3 y to the 3/2, and well, g prime will be, or let me call it f, because I already used f for the formula. F prime of y, that's 3/2 times 2/3, y to the 3/2 minus 1, that's a 1/2. Cancel the 3's, cancel the 2's. F prime of y equals to y to the 1/2, which at the same time is the square root of y. So coming back to the integral here, that's going to be the integral from 0 to 3, or rather 2 pi, the integral from 0 to 3. That's simply y square root of 1 plus the square root of y squared with respect y. So that's our integral to evaluate. Well, let's do some simplification. Notice on the one hand how this square cancels this radical, and so we're going to be left with 2 pi integral from 0 to 3 y square root of 1 plus y dy. So, well, that's the integral that we need to evaluate. Well, so we have a couple of issues here because, well, usually we look for the pattern. Well, when it comes to setting the u du to perform the u substitution, we usually look for the pattern, whatever inside of the parentheses, inside of a radical, or being the exponent of an exponential function, or the inside of a logarithmic function or trigonometric function, it's usually 1 degree higher than what we have outside to multiply with the dy, and that's so we can get the part that stands the du part of the problem. But in this case, well, notice the degree of 1 plus y. In this case, it's a degree 1, and we have a y equals to 1. So the u substitution that we are used to use is not going to work just with those two elements, u and du. So we will need one more element, a third element, or a third ingredient in the substitution. So And you may have seen integrals like this back in Calculus 1. If it's been a while, well, I think it's a good time to go back to review those ways to do the u substitution. So we're going to set u equals 1 plus y. So that's our number one ingredient in the substitution. Number two is du, and du is dy. So no coefficients will need to be changed at all, which is great. Alright, so that's number two. Now, because in this case the degree became degree 0 essentially, and we still have a y multiplying with the dy instead. If we had, for example, 1 plus y squared, the derivative is 2y, well, it would have worked perfectly with these two ingredients in the substitution. So in this situation, we're going to do the following. So what we're going to do is solve for y. And if we solve for y, that's going to be y equals to u minus 1. Okay? So this is how it's going to look like. So that's number 3. And of course, my advice, change the limits of integration also to the corresponding in the world of u. So u of 0 and u of 3. So u of 0, that's going to be 1 plus 0, which equals to 1, and 1 plus 3, which equals to 4. So let's go back to the integral and express everything in terms of u, and also write down our new limit. So that's the integral, that's a 2 pi. The integral, instead of going from 0 to 3, because of the corresponding in the world of u as 1 plus y, this will be 1 to 4. And well, this y, we did a substitution for y, which is u minus 1. And the whole radical, that's the square root of whatever quantity we have inside of the radical, which is 1 plus y, but that became a u. And then du. Okay? So, well, this is how we fix this issue of that pattern not going 1 degree higher when it comes to setting out the u. So, well, let's simplify this integral. So that's s equals to 2 pi integral from 0 to 3 u minus 1 times u to the 1/2. Let's change the rational exponent. Which one? Oh yeah, that's what I meant. 1 to 4. Yes, thank you. From 1 to 4. So the u, so that's 2 pi, the integral from 1 to 4 of u to the 3/2 minus u to the 1/2 du. And we can use just general power rule on this one. Just add 1 to the exponent of 3/2 and divide by the new exponent. Add 1 to the exponent 1/2 and divide by that exponent. So that should be 2 pi integral. Oh wait, no more integrals. So that's u to the 3/2 plus 1. Isn't that a 5/2? 5/2 over 5/2 plus, or minus rather, u to the 3/2 over 3/2. Evaluated from 1 down to 4. Okay? So again, dividing by fractions is the same as multiplying by reciprocals. So that's a 2 pi. That's integral. Oh no, not integral. That's 2/5 u to the 5/2 minus 2/3 u to the 3/2. This is still from 1 to 4. Alright, so let's see about this now. So we may go back and substitute. So 2 pi. So that's going to be number 1. Okay, so how about, well, okay. On the one hand, this will mean the following. This u to the 5/2 means either the square root of u to the 5th power, or the square root of u, the whole thing to the 5th power. Well, which one are we going to use? So recall that we used the first version a few times in previous examples whenever we had a number that it's not a perfect square, but we had higher powers than the actual index. And we use this form in order to factor the quantity inside of the radical and factor out or take the perfect square outside of the radical. So that was when we don't have perfect squares. However, if you observe these two numbers, these two limits, both of them are perfect squares. So instead, I'm going to use the second version because it's easier to evaluate, for example, the square root of 4, which is 2, and raise it to the 5th power. That's going to be 32. As opposed to, for example, instead of having the square root of 4 to the 5th power, imagine having to multiply 4 5 times. That's going to be a really big number, and then on top of that take the square root. That's not going to be an easy task, especially when you're on a quiz or on an exam. You don't have a calculator or the like. So in this case, well, it's important to check whether these limits of integration are perfect squares. So the best way to go about it is by writing in this form, and that's minus, and this one right here will mean the square root of u to the 3rd power. And same, we can take the square root of 4 and the square root of 1. I mean, they're perfect squares, and that's what I'm going to do here. So that's 2/5 square root of 4 to the 5th power minus 2/3 square root of 4 to the 3rd power minus, in this case, this will be 2/5 square root of 1 to the 5th power minus 2/3 square root of 1 to the 5th power. Well, the second term, this second term is going to be relatively easy to simplify because that's just the square root of 1. So, well, that's 2 pi times, or I think brackets would be fine. Okay, so the square root of 4, which is 2 times, 2 to the 5th power is 32, yes. Which one? Oh yeah, this one right here, right? Thank you. 3. Alright, thank you. So this is 32 times 2, that's 64 over 5 minus the square root of 4, which is 2, cubed, that's 8. 8 times 2, that's 16/3. And then minus, okay, so that's simply 1 and 1, so that's 2/5 minus 2/3. And well, simplifying this result should give us, well, I thought I had the result on me, I'll have to do it on my own. So 64/5 minus 2/5, that's 62/5, and negative 16/3 plus 2/3, that's 18. Wait a minute, it's 14/3, right? Minus 14/3. And then multiplying this together, well, I forgot the 2 pi outside. I thought I had the result with me. Anyway, so that should be, okay, LCDs, that's times 3, and that times 5, and times 5. So let me use my calculator. I'm going to use my phone real quick. So that's going to be, okay, our least common denominator of 15 in the first place, and what else? All right, 62 times 3 and minus 14 times 5, which is 70. That should be 116. And then that times 2 pi, that's 232 pi over 15. All right. Yes, weird number with result. Well, ultimately, well, there's a couple of objectives with this example. Notice how this time our functions were given in terms of y and we were rotating about the x-axis. So this is the critical part of the setting up of the problem, where the radius, it's actually just going to be y, and we don't substitute with the actual function, because y, well, we already have an integral in terms of y, so that's fine. Okay, so let's look at one more example. The next example number 4. So we have the arc of the parabola from the point 1, 1 to the point 2, 4, and it's rotated about the y-axis. So we're going to do this problem 2 different ways. So we're going to find the area of the surface by considering y as a function of x, and then by considering x as a function of y. Well, ultimately, we want to show that it doesn't matter how you set up the same problem in functions using functions of x or functions of y. You should get the same result. Okay, so number 1, how about we sketch the region as usual? So this is going to look like the parabola from 1, 1 to 2, 4. So that's going to look like this. And while rotating about what is the y-axis, right? So we're going to do the rotation in this direction about the y-axis. So that's going to give us essentially this following region right here. So which is going to look sort of like this. That's a solid that we would be obtaining. Alright, well, I can make it solid over here. Yes. So let's set up our integral. Number 1, well, number 1, it's in terms of as a function of x. So let's write down the integral for surface area, 2 pi integral from a to b. That's r of x times the square root of 1 plus f prime of x quantity squared dx. So first, the trickiest part again is to write down our radius, our r of x. So in this case, well, let's draw that radius in the region that we just plotted here. So in this case, this radius is going to go from the axis of revolution to any point on the edge of the solid. And notice how this time it goes like this. It's a horizontal line. So, well, what variable represents horizontal distances? X, right? Well, this is a function of x. I mean, this is an integral in terms of x. Well, this is just going to be, it's just x. All right? X units. Well, we also need to take the derivative of this function. Well, so the derivative of y squared, of y equals x squared, is simply y prime equals to 2x. So this will be the integral, or 2 pi the integral from a to b of r of x, which is just x, square root of 1 plus the derivative to x, quantity squared, with respect x. And simplifying the integrand slightly, we should get to pi integral from a to b, or not a to b, that's actually, well, in this case from the point 1 to 2, from 1 to 2, from 1 to 2, and that should give us x, square root of 1 plus 4, x squared. Be careful, because when we're squaring to 2x, and this quantity, this power right here, should affect both the coefficient and the variable. So that's usually a very common mistake when working with this type of problems. We only square the variable, but we tend to forget to square the coefficient as well. Or backwards, we just square the coefficient but not the x. All right. So that dx And well, let's see, it looks like this integral, it's a great candidate for u substitution, not the 3-ingredient u substitution like the one we did in the previous example. In this case, the regular 2-ingredient substitution, u du, because the derivative of 1 plus 4x squared is going to be 8x. We already have that x. All we will need later is just a correction factor set by the du part of the problem. So in this case, u equals to 1 plus 4 x to the 4x squared. That's du equals 8x dx. That means x dx equals 1/8 du. Right? But also, again, we need to change our limits of integration to the world of u. So that means u of 1 and u of 2. So u of 1, that's 1 plus 4 times 1 to the second power, and u of 2, that's 1 plus 4 times 2 to the second power. Well, let's simplify this new limit. So that's 1 squared, which is 1 times 4 equals to 4 plus 1 equals to 5. And 2 squared, that's 4 times 4, 16 plus 1, 17. Well, what are we going to have in this case? So we're going to get the following integral. Let me go back. So that's 2 pi integral from 5 to 17 of x dx, which is represented by the 1/8 du, and the radical, the square root of 1 plus 4x squared, that's going to be our square root of u. And well, so number one, let's do a couple of things in one shot. Number one, I'm going to take this coefficient 1/8 outside of the integral and reduce it with the 2 pi that we have here. That is 2 pi over 8 reduces to pi over 4. That's the integral from 5 to 17, to 17. And this square root of u, it's the same as saying u to the 1/2 du. And we're ready to integrate this function. Again, just add 1 to the exponent, and then divide. Don't forget to divide by the new exponent. So that's pi over 4. That's u to the 3/2 over 3/2 from 5 to 17. So, well, again, number one, dividing by 3/2 is the same as multiplying by 2/3. That means 2/3 times pi over 4. And that's going to be, again, it could be either, okay, again, we need choices here, and we need to consider both choices of the radical version that we're going to do for this. On the one hand, this u to the 3/2 is the same as saying the square root of u cubed, or the square root of u, the whole quantity cubed. And in the previous example, we used the second version because it was easy to first get the square root of the number, and then to get a smaller number, a nicer number, and then square it. However, that's not going to be useful this time, because if you look at the limits of integration, these numbers are not perfect squares. So we will have to use the first version and just break up the powers in a way that we can factor a perfect square. So we're going to use the first version. So that's going to be the square root of u cubed from 5 to 17. Simplifying, the 2/3 times pi over 4, that reduces to 2/4 reduced to 1/2 times 1/3. That should be pi over 6. Alright, pi over 6, and that's the square root of 17 cubed minus the square root of 5 cubed. And yes, we need to reduce these square roots. So we need to break up this 17 cubed the following way. 17 squared and 17, 5 squared and 5. And well, from here we will factor out the perfect square that's going to go outside of the radical. Well, so that's pretty much the breakup. Let me write it down. So that's pi over 6 That's the square root of 17 squared times 17 minus the square root of 5 squared times 5. And well, let me highlight the perfect squares. Those are the ones that are going to get they're going to be evaluated. And well, the square, basically the square root of 17 squared is simply 17. So 17 root of 17 minus 5 root of 5. And that's final answer. So the reason why I'm going through all these details is because WebAssign is going to ask you for final answers looking like this. I don't think WebAssign is accepting like these radicals without being simplified or rational exponents. Well, again, how did I get this? Well, essentially I'm using the product rule of radicals. And the product rule of radicals say, well, in this case, the square root of 17 squared times the square root of 17. Well, in this case, the radical cancels the square, and that's 17 root of 17. So that's how we got that part. All right. Well, that's the first part of the problem. Doing the problem as a function of x. Well, let me label this. Part 1, function of x. Number 2, functions of y. All right, so let's see. So what do we have this time? So we are given the following function. So we're given the function y equals x squared. So the first thing we're going to do is write this function as a function of x. And well, essentially it's a function of y. So in this case, we have to solve for x here. Now, to get x by itself, we need to get rid of the square. How do we get rid of the square, by the way? We take the square root. X equals the square root of y. Should that be our final answer? Am I missing anything? Okay, so technically we're missing a plus or minus. I agree with that. However, notice that we are working on the first quadrant where all values of x and y are positive. Because of this, we don't need to put that plus or minus. Had we worked, on the other hand, maybe on both sides, well, or on the left side, that would be the second quadrant, we have negative values of x, and in that situation we would have used the negative version of the function. So yes, technically we should have placed a plus minus symbol in front of it, but again, because we're working on the first quadrant, we don't need. And in fact, it would better not have this, because that'll be troublesome when trying to compute the integral. We would have to compute two integrals, two separate cases, one for the negative and one for the positive, but again, we are only in the first quadrant. All right, so let's find the derivative. So that's and that x equals f of y. So f prime of y equals 1/2 y to the negative 1/2, which reduces to 1 over 2 root of y. All right, so let's go about the integral right here. So let's see. Number 1, let's write an integral in terms of y. That's 2 pi. The integral from c to d r of y times the square root of 1 plus the derivative f prime of y, quantity squared, dy with respect to y. All right, first things first. So what do we have in this case? So in this case, since from the picture, again, we have a horizontal distance x from the axis of revolution to any point on the graph that we are rotating about that y-axis. Now, so when it comes to, When it comes to determining what r of y is, well, so r of y is an x. Okay, but this x is not the variable that we're working with. In this case, we are working with functions of y, so we cannot have two different variables at the same time. Well, not in this case. Later, when you get to Calc 3, well, you will work with integrals with more than one variable. That's not the case yet. So we need to express x, in this case, the radius, the horizontal radius, in terms of y. Lucky for us, we have a function f of y. So this will be the integral. This will be the integral. Let me make some space. To pi, the integral from c to d. Well, what are the limits going to be this time? Well, if we were given only values of x and y, it would have been our job to figure out the y values by plugging them on the original function. But in this case, we're giving order pairs. So for the limits of integration for this integral in terms of y, all we're going to do is use the y values of the given order pair. So this integral is going to go from 1 to 4. All right. So the integral from 1 to 4 of r of y, which in this case is our given function, square root of y, times the square root of 1 plus the derivative of the function 1 over 2 root of y squared with respect to y. So let's simplify one thing at a time. So number one, what we're going to do here, so let's see. So number one, let's square square root of y times the square root of 1 plus 1 squared, which is 1, 2 squared, which is 4, and square root of y squared. Cancel the radical with the square, that's simply y, and times dy. Alright, so from here there's a couple of ways to go about the next few steps. Well, we could go about so I'm gonna find the LCD here. I'm going to combine the fractions together. So that's basically a 1 over 1 plus, well, in this case we would need to multiply numerator and denominator by 4y. This way we would get the same denominator. So we can write this as a single fraction. So that's 2 pi integral from 1 to 4 square root of y square root of 4y plus 1 over 4y with respect to y. So now that we have simplified this, we're going to use the product rule of radicals again. So we have two radicals multiplying together, the product of the radical a times radical b. That's the single radical of a product AB, and that's what I'm going to do. Merge them into one single radical by this property. So this will be 2 pi integral from 1 to 4, and that's a big radical, y times 4y plus 1 over 4y dy. Well, notice something here. Notice how the y's cancel out, and we're still 1 to 4 integral of the square root of 4y plus 1. That's all we get this time, dy, or actually over 4. Alright, this time I'm going to use the quotient rule for radicals in the same way that we have the radical of a quotient, because this is the radical of a quotient AB. That's the radical of A over the radical of B. Alright, so the square root, we're going to have 2 pi integral from 1 to 4. That's the square root of 4y plus 1 divided by the square root of 4. But what's the square root of 4? Isn't this a nice number? How about just 2? And Notice how these twos divide out, simplifying our integral in terms of the coefficients that we have. And well, let's see what we get. So that's simply pi integral from 1 to 4 of 4y plus 1 dy. And well, this integral we can compute it using the method of substitution for, in this case, u equals to 4y plus 1 du equals 4 dy, which means dy equals 1/4 du. Alright. So, also let's change our limits of integration. So u of 1, u of 4, and that's 4 times 1 plus 1, 4 times 4 plus 1, that's going to be 5, 17, and well, so that's going to become the integral of 1 from, no, not from 1 to 4, but from 5 to 17 of the square root of u, 1/4 du, with the pi outside. And let's take out the pi over 4, the 1/4 to multiply with pi. That's the integral from 5 to 17 of the square root of u du. But wait, isn't that the same integral that we got before in the previous step? So there's no need to compute it again. I mean, why? If we already did it, so where is it? Well, it's actually over 6, but still, when we integrate that 3/2, that's going to become a pi over 6. So again, this result will be exactly the same, pi over 6. 17 root of 17 minus 5 root of 5. So here again, the moral here is it doesn't matter how you set up the integral in terms of x, in terms of y, as long as you rotate the region about the same axis, you should get the exact same volume. As opposed to what we did in the first two examples, example 1 and example 2, in which we had the same region, but in that case we rotated about different axes. On the first case about the x-axis, in the second case about the y-axis. And this is the end of the section actually. Let's see if we have, yeah, sure, we can do something about the next section. So that's actually the end of the chapter. That chapter was very short. It's only 2 sections, arc length and surface area. Well, so what are we going to do for this section? So for this chapter, modeling with differential equation. So what's a differential equation? A differential equation is an equation that contains can you please stop doing that noise? I don't get distracted. Thank you. So it's an equation that contains an unknown function and some of its derivatives. So this time we're going to solve an equation, but we're not going to obtain just a number the same way we got when we solve algebraic equations like rational equations, linear equations, quadratic equations, you know, all those kinds of equations. So this time the result will be a function, not just a number. Well, that function, yes, could be just a number, but in general could be other, you know, a function in general. All right, so what's the idea here? So number one, we're going to have an algebraic equation. Let's make a difference between an algebraic equation and differential equation. So, for example, let's do something simple, nothing crazy, nothing fancy. X minus 3 equals to 5. So the idea of solving an algebraic equation is to find the value of x that makes this statement true. In other words, what number minus 3 equals to 5? Well, it's easy to guess, I guess, at this point. However, when we first learned this, what we did is to isolate the x by doing the inverse operations with the terms that we had besides the x. So add 3 to both sides to get x equals to 8. So that's the solution to the equation. And then when you first learn about the algebraic equations, you were asked to check the solution in order to make sure that it works on both sides. So for example, so let's check. We check, so that's going to be 8 minus 3 equals to 5. So 8 minus 3, that's 5, equals to 5. So because we get the same result on both sides, well, that means this is a legit solution. What about differential equations? And again, let's do something simple. So dy dx, which is the derivative of some function, minus 2x equals to 5. Alright, so in this case, the question is what function whose first derivative minus 2x equals to 5. So we're going to jump ahead and solve for dy dx, and that's going to be 2x plus 5. Okay, so then we're going to do what we call a separation of variables, which is analogous to what we did back in the algebraic equation. So we separated the variables, whatever x, y, or z, whatever dummy variable that you were given, we left those on the left hand side and the constant terms on the right hand side. So here we're going to leave everything containing a y on the left hand side and everything containing x on the right hand side. So in this case, we will multiply both sides by dx. Essentially, we're finding the differential. So that's dy equals to 2x plus 5 dx. So in the same way that we solve the algebraic equation, we were always doing the inverse operations to isolate the x. So in this case, we are doing all the inverse operations to retrieve y. In this case, that is going to be the function whose first derivative minus 2x equals to 5. Alright, so we already did the opposite of subtracting 2x, which is to add it on both sides. We already did the opposite of dividing by the x, which is to multiply both sides by the x. Now, we need to get rid of these differentials. What's the inverse of a differential? The integral. So let's integrate both sides. So we're going to integrate. So the integral of the y is simply y. The integral of 2x is x squared. The integral of 5 is 5x plus some constant of integration. So that's our general solution to the equation. And well, just getting into the vocabulary, this is a general solution because this c is actually any constant depending on the initial condition. So essentially, this will map a picture of a family of functions. So, well, now let's check. So let's check the equation. So, well, this equation is calling for the first derivative of the function, and the first derivative, dy dx, equals to x plus 5. The derivative of a constant is just 0. Well, so coming back to the equation, so what are we going to do? So 2x plus 5 minus 2x, is that equal to 5? That's the question. Well, notice how the two x's cancel, and in the end we get 5 equals to 5. So indeed, this is a legitimate solution to that equation. Of course, this method of separation of variables is not the only method to solve differential equations. There's actually a bunch of methods, but in this class we're just going to go about this method and some applications. All right.